at the University of Cambridge under the supervision of Richard Josa, one of the founding fathers of quantum computing. And Satya's research interests include quantum algorithms and computational complexity theory. So in the following 40 minutes, Satya will talk about quantumly sampling optimized random features to speed up kernel-based methods for machine learning. Let's welcome him.
Thanks, Hao-Chung, for the kind introduction. And also at the outset, I'd like to thank Minshu and all the other organizers for inviting me to speak at this workshop. So as Hao-Chung said, I'll be talking about a method, a quantum algorithm for kernel-based machine learning techniques, which involves the use of random features. So the paper that this talk is based on is archived. It's on the archive last year in April, and you can find it at this this number. And the talk is based on joint work that I carried out with Dr. Hayata Yamasaki, Dr. Sho Sonoda, and Professor Masato Koishi. It was published in Europe's last year. And when I was doing this work, I was still a PhD student at Cambridge, and I was funded by a Cambridge India scholarship by the Cambridge Trust in SERB, just to disclose all my funding. So to begin the talk, I'll start off slowly by introducing what supervised learning is and what random features are. And I'll try to give some motivation for why we're interested in quantum machine learning, and in particular for the context of this problem. I'll then go on to stating the main result of our work and give a brief outline of the ingredients that go into the proof. I know that the previous talk was a quite different flavor, so I'll try to set the tone by beginning with a short introduction to supervised learning. So I'm sure a lot of you are quite familiar with machine learning. The kind of fundamental task in almost all machine learning applications is supervised learning. And what is supervised learning? The goal of supervised learning is to learn a function, an underlying function that maps from input data to output points. The input data could be generally a d-dimensional real vector, or it could also be from other kinds of spaces with different kinds of structure. But in most applications, we're happy to work with d-dimensional real vectors. And the input is obtained from some unknown underlying distribution. So there's some probability associated with any particular input point. So I'll denote the probability measure associated with the input by d rho of x, and the corresponding density function by q superscript rho. The output, on the other hand, is a set of real numbers for our purposes in this talk. It could also be from any other space. It could also be a vector, but we're typically interested in real numbers. And the classic example for this kind of task is when you have images as input data. So images can be thought of as real matrices, so n by n matrices. And the outputs could be labels such as, so for example, if the image is the image of a cat, then you want the output to be either cat or not cat. So I'd like you to keep this image in mind. So the key ingredients are going to be the data distribution, the underlying function, and these two spaces. So in supervised learning, the fundamental task is to learn an approximation of this underlying function f from a few labeled examples of the function. So the number of labeled examples that we use will be called the sample complexity. This is not something that I'll be focusing on in this talk. It's not the quantity that we try to optimize or work with. So maybe just to remind you what the labeled examples are, it's these objects. So x1 up to xn are randomly sampled according to the input distribution. And we are also told what the function values, y1 up to yn. So the y's are equal to f of x. So these quantities are, and these quantities are supplied to us for the input data points. So to proceed, we want to learn an approximation of f from as few labeled examples as possible. Leaving aside the sample complexity part of it, how do we go about doing this? So the first thing we say is we can't really work with all possible functions. So f could be drawn from all possible functions from the set x to the set y, and this is a huge set and doesn't have any particular structure. So we first say, let's focus on some model, some subspace of functions which have nice behavior. So for instance, we might say, let f be could be polynomials of degree less than equal to something, say k. So f is this model. This is what we call the model, capital script f. And from this model of functions, we want to find the best function that approximates the target function. And in what notion do we define the best function? For this, we decide on a quantity called the generalization error. More generally, it's a loss function that we use. In this case, for this work, we just focus on a very simple generalization error, which is given by the average of the error over the data distribution. So this is the data distribution, and we're integrating over the input space. And f hat is our approximation, f is the target, and we want this to be less than some desired precision. And this is what I will refer to as achieving learning to a desired accuracy epsilon. Right, so we know we want to do this. We have f, we want to find f hat, minimizing a certain error. Now, how do we go about doing this? So as I said earlier, we want to use knowledge of some input points, some labeled examples, to predict the function, predict values of the function on unknown data points. So in order to do this, we need some way of extending our knowledge of known data points to unknown data points. One way of doing this is by using this notion of a kernel function. And a kernel function can be thought of as a kind of similarity function. It measures the similarity between two data points. So if we have two random samples, x1 and x2, drawn from the underlying distribution, then the kernel function captures some kind of underlying connection between those points, which is relevant to the data distribution and the function that we're interested in. And I'll also mention that we'll be interested in particular in kernels which have the property of translation invariance. And translation invariance just means that although the kernel is a function of two variables, it essentially depends only on the difference between them. The difference in the sense that, so because we said that x will be d-dimensional real vectors, this is just the Euclidean distance between the 2 points. In principle, it could also be some other distance metric. As long as it's a metric on the space x, we can define a translation invariant kernel by this property. So moving ahead to random feature expansions, as soon as we introduce kernels, the next idea that people have developed over the last 4 or 5 decades in the learning literature is the notion of feature expansions. So this is a bit nonlinear. So the actual idea starts from here. The fact that gives rise to random feature expansions is that the kernel function is usually has some very nice structure, which allows it to be written as an average over feature functions over some distribution on a feature space, what's called a feature space V. So V here, you can think of V also as another subspace of RD. So we started with X as a subspace of subset of RD, and V is also a subset of RD. It doesn't necessarily have to be the same dimension. And the key ideas that we exploit are the properties of the kernel. So the kernel it's a bivariate function. Apart from that, it also has some very nice properties. Aside from translation invariance, it has some very nice properties such as non-degeneracy and it's also positive. Typically, we work with positive semi-definite kernels. And these properties allow us to write the kernel as an average over some additional set of functions which are defined by using this additional space, by introducing this additional subspace called the feature space. And in particular, once we have this feature space, feature functions are defined by a particular VM. So for every value, for every element drawn from V, we obtain a single feature function, which is induced by VM. So phi of VM X, in this case, for example, in this work, we choose phi to be these Fourier features. So they're just exponential of -2 pi I V dot X. So once we have these ingredients, once we have the kernel and feature functions, ultimately we can formulate the target function as a superposition over, well, I'm using the word superposition because this is a quantum talk, but as a linear combination over feature functions. So you can think of this as literally as features of the underlying data. So for example, in the image case that I introduced on the first slide, a particular feature, so for example, let's say one value, one VM is just the vector. So let's suppose V1 is the vector 1, 0, all zeros. This induces a particular feature function, phi of V1 dot. You can think of this feature function as capturing some underlying feature of the data. And in the image example, this could be maybe the background color. So whenever the background color is blue, the feature function phi v1 appears in the expansion for the target function. This is just a very naive example that I'm giving to explain what feature functions do. So the idea is that we write the target function as an expansion over feature functions. And then we have these coefficients alpha I, which are real numbers that we want to determine. And we'll do that by using regression and minimizing the generalization error. So just to remind you, the generalization error was f hat x minus f of x. And we integrate this over all data. And we want this to be less than epsilon. And the regression will be done so as to achieve this condition. So now that we have all of this in mind, random feature expansions have been studied for several years now. And the first breakthrough result was in 2008 of Rahimi and Recht. And they showed that by sampling M features from d tau, a distribution that's defined on the feature space V, we can approximate the target function by using only at most, by using order of 1 over epsilon squared features. And again, just to recall, epsilon is the learning accuracy that we're interested in. So what you notice here is that the dependence on epsilon is not particularly great. In particular, for some kinds of data, when the data distribution is not very good, if this is pathological, and there are examples of interest where this is true, this could scale exponentially in the dimension. So x was dimension d, and what happens is that m in the worst case can scale as exponential in d. And this is bad. Algorithmically, this is very hard. This is intractable. So what happened is in 2017, Francis Bach came up with a formulation where by weighting the distribution, the feature distribution with an additional function that is optimized, an additional density function that's optimized for the data, he showed that we could achieve learning to accuracy epsilon by using only order log squared 1 over epsilon features. And this is in particular an exponential improvement over previous work as a function of the learning accuracy. So the aim of optimized random feature expansions is to minimize the total number of random features that we need in order to approximate the target function. And so we had f hat was a sum over m random features. And this is the quantity that we want to minimize. M is the quantity that we want to minimize. Bach also proved that this quantity, the number of features that he achieves using his method, is optimal up to logarithmic factors. And so this is what we'll be interested in. Going further, we'll be interested in the work of Bach 2017, where optimized random features, data optimized random features, are used for approximating the target function in supervised learning. And data optimized just means that we sample features from V using an additional weighting function, a weighted distribution density function. And so after some discretization and other technical discussions, what we arrive at is this capital Q star epsilon over the, which is a distribution, a density function over the feature space, which has this form. So if you recall, the phi's are the feature functions. And this notation is just to mean that this is the feature function induced by V tilde. Q hat rho is the data density that I'd introduced on the first slide. Data distribution. And this operator sigma here is the so-called integral operator that is induced by the kernel. So it's related to the kernel. I won't go into the details of what it looks like. It's not strictly necessary. It's just a quantity that is directly determined by the kernel. So this Q, so I'm using capital Q here in contrast to small q, because we need to do a bit of work to get here from here, because the whole formulation is in terms of infinite dimensional spaces and operators, and we are finally working with a discretized version of these operators and with empirical density functions. So ultimately, this is the quantity that we're going to be interested in. The quantum algorithm that I'll be presenting works with this quantity, and the goal is to be able to sample from Q star. Okay, so moving on, why are we interested in this method at all? So I only mentioned the case of supervised learning so far, but it turns out that Bach's method, and in general, the method of optimized random feature expansions, is very useful in a wide variety of fields. So in applied mathematics, it's useful in signal processing, Bayesian inference, just function approximation and optimization. And in general, anywhere where any context in which we're interested in the numerical computation of high dimensional integrals. So we typically use quadrature rules or such other techniques to estimate high dimensional integrals, and random feature expansions, and in particular optimized random feature expansions, can be very useful for this kind of computation. And also, as a side note, all kinds of machine learning techniques such as ridge regression or clustering, k-means clustering, they can all be kernelized. They can take advantage of underlying kernels. And then why quantum? Why should we consider this method for implementation by a quantum algorithm? So it turns out that sampling features from this optimized distribution that I defined on the previous slide is quite hard. It turns out to be the bottleneck that slows down classical algorithms. The best known classical algorithm, which is also presented in Bach 2017, requires the inversion of a full rank and non-sparse matrix of which is generally of dimension exponential in the data dimension. And this inversion then requires a worst case runtime that's also exponential in the dimension. So just to recall what this operator was, if you noticed here, we have sigma plus epsilon identity inverse, and it's this integral operator that's the culprit of the classical bottleneck. And what makes it worse is the fact that we have this identity operator that's added on, so that the whole thing, the sum of sigma and epsilon identity together, is a full rank operator, and in general, it can be dense and have other bad properties. Right, so as soon as we hear inversion, we know that quantum computing has been, in the recent years, quantum computing has found great success in linear algebra. So in particular, we have the famous Harrow-Hasidim-Lloyd algorithm of 2009, which achieves matrix inversion in essentially log of the dimension time. Matrix inversion, so what they do is essentially, if A is an n cross n matrix, then you can invert A in order. So this is quantity kappa, which is the condition number of the input matrix, kappa of A times the sparsity of A times polylog of n. And it's this polylog of n that's very interesting to us, because if we could have a method that inverts the integral operator in a polylog of the dimension complexity, then this exponential cost would not be incurred, because of log of e to the d would just be d, and we would have some algorithm that takes linear time in the data dimension. But then we run into a problem, which is that the HHL algorithm and other known quantum algorithms for matrix inversion achieve a speedup only when the input matrix is either sparse or if it has low rank. So what do I mean by sparse here? In particular, it's a very strong notion of sparsity, which is that every row and column of the column of A must have order polylog n non-zero entries. This is a bit of a restrictive assumption. It does turn out to be quite useful in many contexts. For example, when we're trying to use finite element methods, when there's a discretization of differential equations, and in such contexts, the matrices that we want to invert have this property. They satisfy this row sparsity property. But more generally, this is not true. And in particular, in this setting of supervised learning with optimized random features, this is not true. We want to invert a dense and full rank operator. And just before we proceed, I'll also mention that kappa, the condition number, is the ratio of lambda max by lambda min. Lambdas are eigenvalues of A. Okay, so I hope this provides some sense of why we're doing this, why we're interested in a quantum algorithm for optimized random features. So now I'll go ahead and look at some related quantum algorithms. So kernel methods and quantum machine learning, as you all know, has been a very active area of research for the last 2 decades or so. And there's a constant stream of papers coming out in particular on kernel methods. And there's the very seminal paper which came out on the arXiv in 2018, Havlicek et al., where they used quantum enhanced features. So there are quite a lot of works that deal with kernel methods in quantum algorithms, and this is this paper is a nice review that goes over the different kinds of papers that have come out on this topic and the key methods that they use. So if you look at this column, a lot of the methods use variational techniques. Some of them use Grover search, some of them use the matrix inversion algorithm. But it turns out that in particular, none of these works are dealing with random feature expansions. When matrix inversion is used, it's usually a different task that is being addressed. And often it's a kind of principal component analysis that people are interested in. So our contributions in this work are that we find a problem that's suitable to attack by quantum methods, and in particular by using quantum inversion. Secondly, we show, so I discussed that the operator that we want to invert is not sparse and it's of full rank. So we show how to circumvent these two difficulties by using a combination of 2 very powerful quantum techniques. One is the quantum Fourier transform, which we all know is one of the sources of the speedup of Shor's algorithm, and in general, the speedup of the hidden subgroup algorithms. The other is the QSVT, or the quantum singular value transformation. This is a recent technique that's come up in the last 3 or 4 years, for implementing functions of input matrices on a quantum algorithm in a quantum computer. So I'll go into more detail on this on later slides. And our asymptotic speedup will achieve an asymptotic speedup that's exponential. So the complexity will go from e to the O of p, O to the e, O of e to the d to O of d essentially. So this is our work, and this is classical. And the technical tools that we use are the analysis of Fourier sparse operator. So we provide a decomposition of the integral operator into a sparse operator, or rather into an operator that becomes sparse when you change to a Fourier basis. And we also provide a method for those of you who are familiar of block encodings, of constructing block encodings of these operators, which are potentially of more general interest. Right, so what is our main result? So for any d-dimensional underlying data that we're given, so this refers to the subspace, the subset X of input data that we start with. And for any desired learning accuracy epsilon, we show how you can sample an optimized random feature for that data from a weighted distribution Q star epsilon times p tau, which is close to the target distribution that's defined in Bach's work, the optimal distribution over optimized random features defined in Bach's work, to any desired precision delta. And so this is a somewhat weird notion of similarity, but it turns out that this is what allows learning to accuracy epsilon at the end of the day. So if we combine features sampled from this weighted distribution, satisfying this closeness criteria, then we can achieve learning to order error to accuracy epsilon. And in particular, we show that the runtime for sampling a single optimized random feature from this distribution is linear in the data dimension. So this is the part that we're most interested in. And this is the additional thing that comes out. So as you can see, it depends on 1 over epsilon, the learning accuracy, in the second component, and it depends on just the linearly on the data dimension in the first component. So if there's time, I'll go into exactly how this comes out. And yes, so I'd like to draw your attention to the fact that this is linear in the learning. The time for sampling a single random feature is linear in the data dimension, whereas the best known classical algorithm, even for estimating the values of this distribution, require exponential time. Okay, so what are the ingredients that go into constructing this algorithm? So first, we want to, as I mentioned earlier, we first need to break down the method, come up with a discretization scheme, and so on. And then the key idea will be that we define a quantum state which has the values of the optimized distribution as amplitudes. And then we will just measure the state. That will be the strategy. And then we use the properties of the translation invariant kernel to obtain this decomposition that I mentioned earlier. So we break up the integral operator, which is a full rank operator, into components that are easier to work with. And those components will be a full rank diagonal operator and the QFT. And again, the technical tools that go into this are what's called the perfect reconstruction of the kernel, and then a regularization. So for more details, I'll just refer you to our paper, which has all of these details. And then the quantum primitives, the algorithmic tools that we'll use are QRAM, which is a version of quantum random access memory, the quantum singular value transformations method, which I mentioned earlier, and we'll see in more detail, and then the quantum Fourier transform. So let's look at these in a little bit more detail. So just to recall, the optimized distribution, distribution over random features that we are interested in is this quantity. So it's this, I guess you can think of it as an average of this operator, the inverse of the regularized integral operator, over feature functions. And the quantum state that does the job, the quantum state that has q epsilon v, or rather square root of q epsilon v as the amplitudes, is this one. So obviously, I won't go into the details of how we how to see this, but just to say simply, if you trace out the first register, then you'll see that these two expressions will match. I think that should suffice. And so you'll notice here that the operators that pop up, the operators that we'll need to implement in the quantum algorithm are one, the this data density that I mentioned earlier. So I haven't exactly told you what it looks like. So it's a diagonal operator, which you can think of in this form. So it's just q hetero of x. This is an operator. I'll distinguish it by maybe putting a in the bar. And we want to think of this as a matrix. So x tilde lives in the discretized version of the input space. And then this q tau is a normalized version of the input again. And it's again, it's an interesting quantity. It's after we do our discretization and other technical work, it turns out to be a very natural quantity that's defined as something that aggregates the weight over what looks like a lattice over the feature space, in the feature space. And sigma, of course, is the sigma epsilon is the regularized integral operator. Right, and then FD, this is a very crucial ingredient. This is the quantum Fourier transform on a Hilbert space of dimension d. And then the next key ingredient is the decomposition. So here, if you look at this, this is a diagonal operator. These two are diagonal operators. And they're easy to invert. They're diagonal and they're also non-singular, which is an additional benefit. So they're easy to work with. And the Fourier transform, we know, is something that quantum computers can do. And the last ingredient is sigma epsilon itself. And sigma epsilon, it turns out, can be decomposed in this form. So once again, we have Fourier transform and this quantity, which we saw here. So this aggregated weight, and then the square roots of the data density once again. So it'll be this object that the quantum algorithm implements, essentially. So we want to prepare this, we want to prepare a state that looks like this, and that requires the implementation of sigma epsilon inverse and the application of these guys. So that's what our quantum algorithm will be doing. Right, so what's the input model we work with? I think many of you would be familiar with QRAM, but I'll just quickly go over what it is. It's the standard kind of model for access to quantum big data. And so what is classical RAM? It's random access memory. So given an address K, RAM tells you how to retrieve the function value or something stored at that memory address in essentially constant time. So when I say constant time, this means that it doesn't depend on the size of the address or the size of the function value. And we have a quantum version of RAM, which is essentially, if you imagine that you had RAM as a unitary or reversible unitary that can be run in quantum superposition. So you have a set of addresses K, and you have a superposition over addresses with some arbitrary coefficients. Then what quantum RAM does is it allows you to retrieve all the function values for those addresses in superposition. So linear algebra algorithms that use QRAM typically have a complexity that scales with the Frobenius norm of the input matrix. And just to remind you what the Frobenius norm is, it's the summation over the squares of the matrix entries. And we take the square root of that. So in particular, this guy can in general be the dimension of the matrix. So if A is n cross n, then this can be as big as square root of n times norm of the spectral norm of A. So what are we going to use QRAM for? We're going to use it for the data. So the input data is, to remind you, it's x1, it's pairs of data points, x1, y1 up to xn, yn. And it's these guys, the population of these guys that will represent in QRAM. So we're interested in the probability measure. And because we can't directly work with that, we work with an empirical approximation to it. So we have some kind of probability mass function, which we obtain by some classical preprocessing to count the data points and to construct empirical frequencies. And then for those of you who are interested in more details, the QRAM requires an additional data structure, a log n depth binary tree that's used for addressing the data. And this is explained very, very well in Kiranidis and Prakash's work on recommendation systems. So once we have these two ingredients, once we do the classical post-processing and construct this binary tree, we have QRO embedded in this diagonal operator Q, and quantum RAM essentially lets us do this. So using 1 and 2, quantum RAM then lets us, it gives us a unitary that maps some input state, some standard input state to a superposition over this quantity that we're interested in. So just to skip back to the previous slide, quantum RAM does this operation. So it takes a superposition of addresses and fills in the function values at those addresses. Here it's doing something similar, but a little bit more complicated. So I won't go into the details, but the state preparation here, this quantity, these amplitudes can be done by black box quantum state preparation. And an example is Grover and Rudolph, 2002. There are more advanced papers from recent times that allow you to do this, to use QRAM to prepare a state of this form. And then an important point that we should notice here is that the Frobenius norm of this operator, which we should be interested in for the complexity, for purposes of complexity, is unity. And this is because Q is a probability distribution, and it's just, and Q hat is just a diagonal matrix which has square root of Q on the diagonals. So the summation over its values, the squares of its values, is going to end up being just unity. This is going to be very important in the complexity analysis of this algorithm. So the second ingredient, as I mentioned, is quantum singular value transformations. So before going into QSVT, I'll just to give an overview. This technique was first introduced to study the Hamiltonian simulation problem, which is, so very quickly, given a Hamiltonian H, we want to simulate time evolution under this Hamiltonian for some input state psi in, for some arbitrary time input parameter to within precision epsilon. So this quantity psi tilde at t is going to be obtained by doing a Hamiltonian simulation algorithm. This is the target, and this is what the algorithm will be doing in Hamiltonian simulation. So as you can see, it's the key object here is a function. It's a matrix function. It's the exponential function of the Hamiltonian H. So these techniques of using matrix functions for quantum algorithms have gained popularity in the last 10 years or so, since the induction of the matrix inversion algorithm in 2009. And so what I want to introduce is what's called a block encoding of a Hermitian matrix A. So you'll recall that quantum computers can only implement unitary dynamics. Closed systems can only implement unitary dynamics. But sometimes you'll be interested in Hermitian matrices. And our example is a case in point. The operator sigma epsilon is hardly ever going to be unitary. So we need to be able to implement Hermitian or non-unitary functions for some purposes. And the simplest way that you can think of for doing this is to expand the space to add some additional ancillary qubits, such that on the larger space, we can have the target operation, the target non-unitary operation, as a block which is encoded into, for example, the top left subspace of this unitary. So these are called block encoding. So UA is a block encoding of A in this context. And what we use block encodings for, it's to to implement the inverse of the integral operator. So quantum singular value transformations is this technique that was studied in detail by this paper, Gillian et al. From 2018, 2019. And they show in detail how, starting with a block encoding, a unitary block encoding of some Hermitian matrix A, you can construct a unitary block encoding of f of A for some well-behaved functions f. And how is f of A defined? Just again, this is perhaps basic, but just to be, this is just the function value applied to the eigenvalues of the matrix. So we can start with either the singular value decomposition and make a definition, or with the with just the eigenvalue decomposition, the spectral decomposition of A, and then define these functions. So we'll be using this. We use this technique to implement this object, sigma hat inverse. And again, to recall sigma hat inverse, we already showed how to decompose sigma hat into simpler components, which is a diagonal matrix and the Fourier transform. So in particular, to implement the inverse, or to implement a to the minus half, we require something that scales as kappa times polylog of the dimension. So this is already good. This looks good because we don't incur any exponential dependence in the dimension. And kappa also we can show explicitly for our purposes. We're interested in kappa of the condition number of sigma epsilon. And we can show that this is bounded by some nice quantity. Again, for these details, I refer you to the full paper. So the last ingredient then is the Fourier transform. And so just to recount in words, the structure in the sampling problem that I've hopefully demonstrated to you on the previous slides, the structure including the properties of the kernel and its decomposition into Fourier transform and a diagonal matrix, allows us to use these powerful ingredients, which is the quantum Fourier transform and the quantum singular value transformation, to avoid sparsity and low rank. So again, the operator that we're inverting is sigma epsilon minus half is dense and full rank. Full rank because it's regularized. So this paper used Haro, Hasidim, and Lloyd. They used sparsity as the key ingredient, and these two, quantum principal component analysis and quantum recommendation systems, quite famous papers that you must be familiar with. These used assumptions of low rank input to achieve exponential quantum speedups. And the classical Fourier transform on dimension n requires n log n time. The fast Fourier transform. This is something I think is familiar to people from signal processing, for instance. While the quantum Fourier transform requires only log squared of n time. And this is the key speedup that, that makes Shor's algorithm possible, for instance. And at a high level, essentially the translation invariance results in a circulant matrix structure. So circulant matrices are like, are these matrices where you have a shift of, so when you have, for example, A11, A12, A13, if the second row is shifted by one element, so you start with A13 and then you have A11, A12, this is a circulant matrix structure. And it turns out that circulant matrices are diagonalized by the Fourier transform. So FFT, FFT, dagger, this gives you a diagonal matrix. And then once you have a diagonal matrix, it turns out to be quite easy to invert. So from here, we can do minus half quite easily. And then we go back and do undo the Fourier representation. At a high level, that's what happens in our algorithm. So we take advantage of the sparsity of this regularized integral operator in a Fourier representation of the feature space. Right. So yes, why is this important? why is our contribution of removing, of circumventing sparsity and low rank assumptions important? It boils down to a lot of recent work, of breakthrough work of Evan Tang et al., and then follow-up papers. And in fact, the morning session had a very nice talk on low rank linear algebra, classical. So there's this whole field of quantum inspired classical algorithms, which show how to exploit low rank assumptions and the use of QRAM via a classical L2 sampling assumption, which is analogous to QRAM, to dequantize quantum speedup. So what happens in dequantization is that if you have a quantum algorithm that achieves exponential speedup, you can come up with a classical algorithm with the same speedup. And the key thing is that the QRAM is a very powerful device, and there's an analogous classical assumption which we can make, which costs the same as QRAM, and this is L2 sampling. Again, I won't explain what that is, but making this assumption, it turns out that you can dequantize some quantum speedups. And because we work with a full rank operator that can also be dense and have large spectral norm, these existing dequantization techniques are not applicable in any obvious way. And I think it's an interesting open problem to see if we can take inspiration from our quantum algorithm to come up with a classical algorithm that achieves the same exponential speedup for sampling optimized random features. So we're nearing the end of the talk, and I've shown you how, I've tried to motivate how we can sample optimized random features. So once we sample the VIs from Q star epsilon, these are the optimized random features. And then we decide the feature functions that we're going to use. We then use stochastic gradient descent for regression to obtain the coefficients. So again, to recall, we had f hat was the sum over alpha m. I'll just call these phi vm for now. So we need these coefficients. And this is obtained by regression to minimize f hat minus f. And so it turns out that this can also be done in classical linear time. So the bottleneck is this sampling is the real bottleneck for classical algorithms. And this is what we speed up in our quantum algorithm. And then after that, once we achieve that and achieve all the random features, we just fall back to classical algorithms. So we need to do a little bit of work to show that in particular, by using doubly stochastic gradient descent, we can achieve this linear time for regression, and that doesn't cancel our speedup, the quantum speedup. So that essentially finishes my talk, and I'll just give a quick summary. So we've identified a niche where big data has small Frobenius norm and is suitable for the use of QRAM. And we deal with a non-sparse and full rank operator that we show how to invert by taking advantage of this operator being sparse in a Fourier representation in conjunction with the efficiency of the quantum Fourier transform and the technique of quantum singular value transformations for implementing matrix functions. And then we show that, of course, this speed up can be useful by doing classical regression. Also in linear time, we don't cancel out the exponential speed up obtained by the quantum algorithm. And this combination is promising because it has been quite hard to identify problems where quantum speedups are genuine and we get really useful applications, or perhaps for want of a better term, applications that are useful for daily life. And our method provides a promising candidate. It does have one big drawback, especially in the near term. It is not at all NISQ friendly because our focus is on provable asymptotic complexity, and the resulting circuits, because of the use of QSVT and QFT, the resulting circuits are actually quite large and would require thousands of qubits even for a binary classification task. And of course, the quantum singular value technique is again requires long circuits and long coherence times and fault tolerance, which are not something that we expect to achieve in the NISQ era. So there are many open problems that this throws up, in particular, like specific applications of our framework. So the framework is in general applicable to quadratures in supervised learning. But it's interesting to see how this can be applied to just classifiers, binary classifiers, or singular vector, support vector machines, and different kinds of regression, and to see what particular speedups are obtained for these problems using this method. And a more interesting and open-ended question is other applications where an operator that is dense and of high rank is sparse in a Fourier transform basis. And because in such applications, we can take advantage of our techniques to implement perhaps other kinds of functions of these matrices and speed up other kinds of algorithms. And another problem that's quite interesting and is very useful is to get rid of the QRAM input model, because QRAM is quite an intensive and powerful model. And in particular, recent research has shown that using only classical access, it has been possible to achieve genuine quantum speedups for supervised learning using purely classical access to input data. So it's interesting to investigate if in our framework, we can get rid of the QRAM, the requirement for QRAM. And finally, of course, investigating the potential for NISC is always something that's a curiosity in today's world. And this would only be feasible in a QRAM-free model. So this perhaps presupposes that we've already done this and then optimizing these circuits for NISC applications. And so that's basically the end of the talk. And for more details, you can look at our paper in NeurIPS or the paper on arXiv, and also there's many more wordy explanations in my recent thesis. So thank you. And I think I've gone over time. I unfortunately didn't have a timer on my desktop. So thank you all for listening very patiently.
Thank you, Sathya. Okay, so any quick questions? Yes.
In the definition of RAM and QRAM, why the retrieval time is taken to be 01? For example, if the size of the address is very long, will it takes more time?
Right. Yeah, I think that's a good question. So I think the key here is that we want. So when I say O1, it's not strictly that it's address independent. I shouldn't have said address independent, but what I meant is O1 independent of the size of f of k, as the size of the value that is stored at that address. Does that make sense? So I think what you said is right. If the address is quite large, so if we have a very large array of RAM, then the addressing mechanism can depend on the size of k. So this could have a weak dependence on k. But nevertheless, it would be independent of the data that is stored at that point.
Okay.
Okay. Any other questions?
Okay, and thank you for providing for introduce this kernel-based quantum machine learning method. And I want to ask, because this is very different from the classical machine learning, and I want to ask, in which part they apply the similar trick of just like in classical machine learning, we define the loss function, and we do the optimization. And I want to ask, I think in this quantum machine learning part, and they apply the something like the stochastic gradient descent, right?
Yes. So stochastic gradient descent by itself is also is one of, it's just essentially a popular optimization technique, which is also widely used in classical machine learning. So stochastic gradient descent in our method, stochastic gradient descent only comes into the picture at the last point. So just to go back, so as I mentioned, we want to find this approximation, and these are unknown. So the alpha 0 up to alpha m minus 1 are unknown. And to determine these alphas, we are going to be interested in the generalization error. So this is the loss function in this case. So as you mentioned, the loss function in classical machine learning. In our case, this is the loss function. So we perform stochastic gradient descent on this quantity to optimize this quantity. To optimize loss as a function of alphas. I hope, does that make sense? Is this what you were asking?
Yes, I think it's my asking.
Okay.
Thank you.
Okay, since it's about time, so let's thank Sathya again.
Thank you.
Thank you, Sathya. I think we should talk at some point.
Yeah, would be great. Thank you. Thanks, Hao Cheng.
Okay, so I think that's today.